So sum of finitely many non-negative integers is 0, which means each one of them has to be 0. Today we'll see an elementary but useful result related to sets and functions. So here we have the statement. Let A be any finite set and f A to A be any function, then f is injective if and only if f is surjective. Before we get into the proof, let me quickly recall some relevant definitions of sets and functions. So let x and y be any two sets and g be a function from x to y. Then for any subset b of y, the inverse image of b under the function g denoted by this symbol g inverse b is defined by those x in x such that g of x belongs to b. Indeed, this inverse image is subset of x. This is also called a pre-image of b or the pullback of b under the function g. In particular, if b is singleton set, then this element, this set g inverse b is what we call the fiber of b. This inverse image satisfies the following properties. Number one, if we take pullback of the entire codomain set, then we will get the domain set, that is g inverse of y equals x. Then pullback or inverse image of two disjoint set is again disjoint. So if b1 and b2 are two disjoint subsets of y, then their pullbacks are also disjoint, quite obviously. Now suppose you have a family of subsets of y, arbitrary subsets family, I mean the lambda is an arbitrary index set. So be any family of sets then g inverse of union of b alpha is exactly equal to union of g inverse of b alpha. And finally note that G is injective if and only if each of the fibers can have at most one point. So if and only if G inverse, fiber, each fiber has cardinality at most one, so less equals 1 for all y belongs to y. Similarly, G is surjective if and only if each fiber has at least one point or each fiber is non-empty. So we'll be using all these facts to prove this result. Okay, so let's try to prove it. So given that A is a finite set, so let's take it to be some, give some name to the elements. So let A equals A1 till, suppose A has n elements, an, then here the codomain set for this function f is A, so inverse image of this entire set is this set. So here A equals f inverse of A. A equals f inverse of A. Now this set A can be thought as union of all singletons, all its elements, right? Now let's use this thing, then it will become union of f inverse of ai, I equals 1 to n. Now since these are all distinct points, so these are all disjoint sets, right, by this. So we can use the notation of disjoint union f inverse of ai, I from 1 to n. Alright, now you take cardinality on both sides of this and this, then we'll have cardinality of set A is n, so n equals cardinality A equals, so since this is disjoint union, so cardinality of the union will become sum of the sets. So summation cardinality of f inverse of ai, I runs from 1 to n. Let's denote this equality by star. Okay. Now what we have to show, if is injective, if and all if surjective. So let's assume first that if is injective. So assume if is injective, which means by our observation, injective means each fiber can have at most one point. So then each fiber f inverse of ai is at most, cardinality of each fiber is at most 1 for all I equals 1 to n, which means 1 minus this cardinality is greater equals 0 for all I. Now by this star, using star, we have, so what about this sum? 1 minus this cardinality. Now you have n many ones, so when you break it, you will have n minus summation of f inverse ai, I from 1 to n. So by star, these two are equal, so this difference is 0. Okay. So now what you have is the following: sum of this n elements, n integers equal to 0, and each one of the integer is greater or equals to 0, that means non-negative. So sum of finitely many non-negative integers is 0, which means each one of them has to be 0, because if any one of them is strictly greater than 0, this sum would have been strictly greater than 0. So we have each one of the summand is 0, that is f inverse of ai, and its cardinality is 1 for all I, which basically tells us each one of them is non-empty, each fiber is non-empty, and which is surjective, surjectiveness of f. So this implies f is surjective. So we have shown that if f is injective, then f is surjective. Now let's try to prove the other way. So conversely, let F is surjective. Then again by our observation, G is surjective if and only if each fiber has at least one point. So then cardinality of F inverse of AI or greater equals 1 for all I equals M. Alright, so again just like before, that means F inverse of AI minus 1, that is greater than 0 for all I. Again using this star we have let's consider sum over all these elements. So this will become summation cardinality of these fibers minus n many 1, that is minus n. So by star these two are equal and therefore this difference is 0. Now again the similar argument, since each one of the summand is greater equals to 0 non-negative and sum of finitely many non-negative terms is 0, each one of them has to be 0. So this would mean cardinality of F inverse AI equals to 1. That means no 2 point maps to the same element and that's your injective. So that means F is injective. Okay. Now we'll see that this result is not true unless A is finite. So let's have some examples. So let's take A to be Z and we define this function f from set of integers to set of integers defined by f of x equals 2x for all x in Z, which means that range of this function is only even integers. So odd integers doesn't have any preimage, which means it is not surjective, and it is injective of course because 2x equals to 2y would imply that x equals y. So clearly then f is 1 1 but not on 2. Now let's take this example. Let's take this function g of x equals floor of x upon 2. Then you can see that for any integer m, g of 2m and that next odd integer, that is g of 2m plus 1, both are equal to m, which means every integer here has a preimage and it has exactly 2 preimages and therefore it is surjective but not injective. So then g is on 2 but not 1 1. So with this, let me conclude today's session. Thank you for watching this video. See you next time.